means it is. So what is the, okay, after we are able to generate AC signal with the help of the EMI topic, like with the help of Faraday's law, we are able to generate an AC signal. Then after that, so what we have come for how to measure that particular signal. How to measure that particular given signal. So that what happened, we took help of AC circuit here. So next question comes like how to distribute it, means how to transfer, how to send from one place to another place. But if you look at the requirement of the AC signal for us, say the transmission point. So let's just go for some small basic circuits. So this is the power station. This is a power station. Which will generate an AC signal. And this is the town. Where in the town what will happen, it has to be distributed. So there's a town. Then what I do is I'll connect a cables, because to transfer power, no, I'll connect a cable. So the cable will have resistance, because it's a conductor basically. And if AC signal flows through a resistor R, will there be any power dissipated? Yes, there'll be power dissipated. So therefore, what shall I do now here? And look at the length of the cable. We have Telangana major source, Ramagundam. The next another major source is what? Srishalam Idle project. From there, the power has to be transferred. Now, you look at the from Srishalam to Hyderabad, 190 kilometer on the cable. Definitely, a lot of power will be lost in the transmission itself here. No, this is a cable. No? These are the cables. Sir, we'll go for low resistance cable. Whatever you do, 190 kilometer length of the cable will offer very high resistance. So when the current flows through it, how the current will flow in this direction, and the reverse path should be like this, no, closed path. And here is what the dissipative element. This power station will act like a source. The cable will offer resistance. So it is just understand some practical way this one. It will be very easy for you, like a why we are, and this is that town. Town will offer resistance, and this is the power station. This is a town. Okay, no, there's a cable. Current, is it justify showing current to the cable? So we'll call this a phase and neutral. Am I right? In the wirings, called as phase and neutral. Now let's come for this. What is the biggest problem? The resistance of the cable, no? So shall we minimize resistance? There's no other way. At least there'll be some resistance. And if I go for like this, if I transfer, so there'll be a lot of power lost will be there. So for that, what I should do? First, what is the requirement in our home? How much of AC voltage is needed? 240 volt, no? 240 volt is needed. Then if I send this 240 volt here, and the cable will have resistance. So almost what happened, what all we send, 90% will be lost in the cables. Means here if I generate 1000 watt, by the time it reaches the signal reaches the town, it will become only 100 watt. The 90% will be lost by the cables. So what to do for this? So let's come for the power dissipation. P equal to V square by R. Instead of I square R. So let me look at the V square by R. Now if I transfer the same power at high voltage, is the problem solved? Then for I voltage, what we can do? So at I voltage, so let's come for this. I equal to R equal to V by I. So what shall I do now? So what is the power losses? The power losses is due to I square R. I think I'll come like this. Power losses in the wire, in the cable is I square R. there's a power loss in the cable. Then we have some mathematically from Ohm's law we can write V square by R. So now somehow what happens if I transfer the power such that if I is very small or if I make I very low, then I square R, the power transferred by the cable, what happened? The power dissipated by the cable can be minimized. But sir, like how do you can, the power which should be generated, how if you send it low power? So what I do is like, power is V into I. Just understand the logic, it'll be very easier. Power is what? V into I. Now, if I transfer the same power at high voltage, low current, so can I minimize the power losses in the cable? Please understand the logic here. If I transfer the power P, at high voltage and low current, then what is the power losses in the cable will be minimized, no? So how to send this high voltage? Means like how much we needed? 240 volt. If I send it 240 volt, almost 80% of power will be lost here. So I should send it high voltage, but we need 240 volt. What shall I do? At power station, and 1000 watt has to be generated. So what I do here is like 10,000 or say like a 10 to power of 5 volt is what I'll generate voltage. Then how much of current should be? Current, this is the voltage. What about current? Will become 0.01 ampere. You multiply these two, power how much it will be? 1000 watt. Is it okay? I'll write Vs and Is. So I'll generate the power of 1000 watt, and I'll see that it should be at, the voltage will be very high and the current will be very low, but overall power is same. This I'll transfer this particular signal where the voltage is 10 to power of 5 volt and the current is 0.01 ampere. This what will happen, I will transfer on the cable. So what is the current? 0.01 ampere. Instead this, shall I do like this? Another alternative, I'll go for it. Power is same 1000 watt, but the source voltage I'll make it 100 volt and the current is 10 ampere. Tell me like which pair of which set of signal will minimize the power transmission or losses during power transmission? Straight away I'm going to conclude this topic. If I transmit signal of 100 watt power with voltage 10 to power of 5 and the current 0.01, the power loss in the cable will be minimum, and that power will be transmitted. There will be power loss. Clear this. If I transmit the signal like this, so what is the power? And the same 1000 watt. But what about the power losses in the cable? It will be maximum, no? And this is unwanted. The power loss in the cable is unwanted. Sir, what happens here? Okay, we'll send like this, 100 volt. Yes, 100 volt. Okay, some which I can use for applications. Let's assume that. Now, if I send it 10 to power of 5 volt, when the same signal arrives here, 10 to power of 5 volt, what is the problem here? How much we needed? Say let's 100 volt is needed. So 10 to power of 5 is something very high, equipment will burn out. So what I do, I will step down it from 10 to power of 5 in a, from say like it's a 1 lakh, no? From 1 lakh, I'll convert it into say like a around 10,000. From 10,000, I'll convert that into 1,000. From 1,000, I'll convert into 100. Like a, I'll step down it. So therefore, what is the requirement now? Something to minimize power losses during transmission, power losses due to transmission in the cables. I should transmit AC signal with high voltage and low current. But at the town, what is the requirement? We need low voltages. So what I should do, when the signal arrives at the town, what I should do, I should step down from 1 lakh. I should bring it to say like a 20,000. From 20,000, I'll bring it to 2,000. From 2,000, I'll bring it to 1,000. From 1,000, 500. From 500 to say like a required 100. Like this, I'll step down it. So to step down this, what happen? I need equipment. That equipment is now called as a transformer. And also again, what is the problem? Can we really generate like a EMF of 10 to power of 5 volt? The answer is no. What is the EMF we can generate? Say 50 volt. How that 50 volt potential difference which is generated is made 10 to power of 5. I should step up I should increase that amplitude of signal. Means like a 100 volt is what AC signal generated. That 100 volt AC signal open, I should convert into first from 100 to 1000, from 1000 to say like a 5000, 5000 to 10,000, then 20,000, then 50,000, then 1 lakh. Then I'll transmit. So at power station, what is needed? We cannot generate high voltage signal. We can generate up to 100, 200 or 300 volt. That should be converted into high voltage signal. Then that high voltage signal and low current should be transmitted in the cables. Then at the town, what is the requirement? Low voltage signal. The same power. Power is same. Don't disturb the power. 1000 watt. Here also 1000 watt. There's no change. But so low voltage signal is needed. Let's say that 100 volt. I should decrease that voltage here. So what is the requirement now? I need an instrument which can increase the voltage and which can decrease the voltage without consuming power. Sir, will use potential divider. No, potential divider will consume power. So that is the reason why we are bringing the transformer here. Are you able to understand? This is just a logic here. So let's come for this one. So what is a transformer? It is basically made up of a core. So what is this? This iron rod, this iron frame. You can take this one. I'll wound turns. I'll wound turns here. There's a copper wire. I'll wound it. It will become similar to like a solenoid. So this is called like a primary part of the circuit here. I'll apply that required AC voltage. You can see here. I'll apply that required AC voltage. Then here current will flow. When current flows here, how B bar? I'll show everything in the diagram here only. It'll be easy for you. So since the current I is flowing in this direction, so apply right hand thumb rule. So the B bar should be here in this direction. Now, what is a there's iron core. So what is iron? What all magnetic field which is set up generated at one point will be transmitted throughout its structure. Means what is the basic thing? Suppose in an iron rod. This will discuss in terrestrial magnetism. Magnetic metal there will discuss. Time being, if I generate a magnetic field here at this particular point, that magnetic field will get transmitted. It will get transmitted here. Here I took a shape like this here. So it will get transmitted. The same magnetic field what we are generated here in this region, this magnetic field what will get transmitted. Why it will get transmitted? Because the iron is a ferromagnetic substance which will transmit that magnetism. So I am not generating the magnetic field at the total structure here. At one point, if I generate magnetic field, that magnetic field will get transmitted. So here what the magnetic field will get transmitted here. So that magnetic field into this area of cross section, it is having area of cross section here. No? Try to understand this. So this will be the area of cross section. So what is the flux now? B into S. So this will have area of cross section. So that yellow color strip, I'll just show it here. This part will become area of cross section. And here, if you want, you can take here also like. For this vertical part, it'll be like this. So for this horizontal part, it'll be like this. So B into S will become flux. So what flux that is generated here, that flux will be transmitted. And the same flux is made to link here. Able to understand now? And it'll get transmitted. So like this, the core is so adjusted that what flux generated in this coil, the same amount of flux is made to link the other coil. I'm going to send a varying current. I'm going to send a varying current. And because of varying current, the B bar will be variable. If current varies, the B bar will be. If B bar varies, flux varies. Varying flux will link this particular coil. According to Faraday's law, EMF will be induced. And that EMF induced, due to that, what a current will flow here. The current will flow here. So now again the current will flow. So here we'll get a current here. And nothing but an EMF will be generated. So I'll put a here only. I'll transmit this to next page. come for this. So it will be, so here the same EMF will be generated here. This will be VP, this will be VS. So EMF induced. So what is the basic, the condition? There's a primary coil. This is called like a secondary coil. This one, and so like this will generate it. So now what is the basic, the working of this based on mutual inductance? Shall I put it here? It just works based on the mutual inductance concept. Total flux linking the primary coil, it is linking the secondary coil or secondary winding. Anything you can write it here. So let's just get into the mathematics. EMF induced in the primary coil, EP, I'll write it. This should be equal to number of turns N1 into d phi by dt. EMF induced in the secondary, number of turns into d phi by dt. Now the flux linking the turns is made constant. Not the EMF induced in the coil. How do I can make flux linking the, that one? You see like this is B bar, B into S, B into area of cross section. The same B into S, what happened will link here. So B into S, and B is in fact variable. So therefore rate of change of flux linking the primary is equal to rate of change of flux linking the secondary. So from this, what we can write d phi by equating these two. So what we get is NP, you call NS, EP by NP is equal to ES by NS. So I want a secondary voltage, that one. So ES is equal to EP by NS by NP. Will they be in phase as how you wind it? How you are going to do the winding, that one. So based on that, so it will be there. So now current here, the winding should be such that the VS will be always made in phase with the VP. So therefore I just put a dot. So what does it mean? It will be in phase, that one. The secondary voltage will be in phase with the primary. Like this, the winding will be done. And what all flux generated in the primary, the same flux is made to link the secondary. How? By iron core. So therefore, the rate of change of flux linking the primary is equal to rate of change of flux linking the secondary. So I'll get this one. And now I want step up, because yes, step up is needed. So here first, E primary is how much at power station, 100 volt I generated. Then it has to be step up to 1 lakh. Or say 1000 volt is needed. So what shall I do for this? I'll just supply this energy to the primary EP. The number of turns of, what shall I make number of turns of secondary? Should be more than that of primary or less than? Number of turns of primary is say like a 20. How many number of turns of secondary should be? So shall we use this formula? According to this formula, secondary voltage is 1000. This is 100. Number of turns of secondary, and number of turns of primary is how much? 20. 200. So when you make number of turns of secondary 200, yes, the voltage from 100 volt is as made it 1000 volt. So let me draw a rough diagram. This is number of turns of primary. This is secondary. How much of voltage here? EP. And here it is ES. So like this, what this is called like a step up transformer.
Sir?
Okay, let me finish off that, then you can ask other things. So let the current here be IP. Let this be IS. Means what we are we violating the energy equation? Nothing. So what is EP into IP? What is the power at the primary? This is a primary. This is secondary. So what is the power at the primary? Power at the primary is Let's talk about the power also. And I'm keeping this. Yeah. So what was the power available at the primary circuit? That should be equal to power available at secondary circuit because energy should be conserved. What is the power available at primary circuit? EP into IP. Power available at the secondary, ES into IS. So when you step up, when you increase the voltage from 100 to 1000 volt, in fact, what should decrease? The current should decrease. How do you can see? Let's write the equation for IS here. IS equal to EP by ES into IP. What is EP by ES? NP by I. So let's calculate now the total power what we sent is say like a 100 into, so this will be 200 watt. So what is the power of the primary? So here only let me work out here. So EP is equal to how much here? 100. So this should be equal to 2. The secondary voltage is what required 1000. We'll calculate IS. So how much it should be? 0.2 ampere. So at the cost of increasing voltage, what will happen to the current? Current will decrease here. So in step-up transformer, when EP ES will be greater than EP. So therefore, IS will be less than IP. So overall power will remain same. How much of power that was there in the primary coil, that much of power will be there in the secondary coil. We are not creating energy here. So what this transformer does, it will just do adjustments between the current and voltage here. So step-up transformer, what it does, it will increase the voltage at the cost of decreasing the current, but overall power will remain same. So what about the current? There's a formula, NP by NS into IP, that one. Is it okay? So expression for the current in the secondary coil, it depends. So shall I say it all depends upon number of turns in the primary and secondary? Symbols what we use, capital. I'll make it capital. So the ratio of turns of primary to secondary, that will determine. So what you can do, step up or step down, that one. No, here what was the thing? So at power generation, what I do, how much of power generated? 200 watt. Then how that is generated with 100 volt and 2 ampere. There's a power. Then it has to be transmitted. So therefore, 2 ampere is a large current. So what I do, I'll convert that into 0.2 ampere. So for that, what shall I do? I'll use step-up transformer. Then using that weapon, from 100 volt, I'll make the voltage as 1000 volt. Then the current, how much will become? 0.2 ampere. At least now the losses will be minimized. No? Earlier, if I send this signal, with power 200 watt, voltage 100, and current 2 ampere, I square R losses will be more. Instead, if I send voltage like this, 100 volt, yeah. Instead, if I send like this, 100 volt, 0.2 ampere, then what when the power losses 0.2 square into our power losses are minimized no during transmission. That's why at the point of generation weapon, I'll use step-up transformer. The signal which is generated at 200 or 100 volt, I'll increase it. Usually we'll transfer by 2 lakh, 10 lakh volts. A very high voltage will be transmitted. Then at the receiving end, how much we needed? We needed maybe 50 volt. Maybe I need 200 volt. What I should do? I should step down. For step down, what happen? What I do is the step down transformer will be like this. This will be primary. This will be secondary. Again, the polarities, put it in the same way. Then what is the basic formula here? So this should be equal to EP equal to NP. Directly I'll write it again y to this one. EP by, so it should be equal to EP by NP should be equal to ES by NS. So what is ES now? ES should be equal to NS by somebody doubt. Let me check it. Step down transformer it is. Yeah, what I do is like number of turns of secondary, I'll make it less here. If I make number of turns of secondary less here, then ES what happen will become less. High voltage should be made low voltage. So step up transformer open NS will be greater than NP. Step down transformer NS will be less than NP. Accordingly, adjust the ratio. So how much of voltage you need a lower voltage. Corresponding OP you can adjust it. But the current here will be say IP. This will be IS. Then all together power at primary should be equal to power at secondary. So this should be equal to EP into IP. This should be ES into IS. So here what will increase? If you step down, the current IS will increase. IS will be greater than IP. ES will be less than EP. So how much desired ES you want will determine the ratio of NS by NP. Like this, the step down and step up transformers are used here. So what shall we do now? So how to increase the voltage? This is the method. Got the idea, no? I think there's in AC circuits, there's a part of that one. So if I check the question papers, no, in AC circuit, which is important? Transformer is important. So, but sir, so many things are there. After transformer, next what is important? Resonance is important. Then all the numericals what we did may not be important for the main circuit. Just basic idea is enough, that one. But the theoretical ideas here, everything you should learn clearly. Mains preparation is totally a little bit complicated. Complicated in the sense like a student should not get carried by emotions. Strategically, you have to prepare for mains exam. I'm not talking about the weekend exam. Weekend exam is just is a training for again advance. Final exam papers, you check it, no? They're just asking the priority in entire AC circuit. The first, you can put like two things, transformer and resonance. Next comes all other things. Advanced development transformers are not there, and the resonance is just a part of that one. So what all numericals we discuss now, they are the priority. The preparation for mains advanced, little bit, you should able to differentiate. Okay, now everything is same because even the mains papers also we are getting advanced level. But final exam, so when you once enter into the grand test now, you can see the difference between mains and advanced. Drastic low level things will come for mains. So for mains, actually the theoretical ideas and the formulas are very important. And the topics which you feel very important may not be very, very important. Just I think it's a simple formula. So like this, the primary step down transformer, the number of turns of secondary should be less compared to primary. In the step up, number of turns of secondary should be more than primary. And transformer will obey the law of conservation of energy principle. S. Basically it obeys here. So this is about the basic structure here now. So why it is being brought? The only purpose is like the during transmission of AC power, the power losses due to the high square R due to resistance of cable should be minimized. Therefore, I should transmit AC signal at high voltage, low current. So how to increase to high voltage step up transformer? At the requirement place, how to step down by step down transformer. Like this, the step up and step down transformers are used here. Okay, next again, we'll see that what is the efficiency of transformer? 90%. Then remaining 10% means around from 98 90 to 99% are there. In India, you know, BHEL, Bharat Heavy Electrical Limited. You look at the shares of that, it will never come down, no? The shares of that stock market. You look at that one, the BHEL. The reason for that, because it will supply almost for another 40 countries, for all the Africa, South America, that one, the South Asia, Iran, Iraq, Afghanistan, for Saudi Arabia, this one South America, then Arab countries, then Philippines. So all such countries know what happened. The India is supplying the transformers and a huge demand. Every year, what when the demand is high, that's why what when the shares, the stock market of this is always increasing. You see that one, and they every with every passing day, what happened? They are doing research and they're trying to improve. So the BHEL transformers, what we have is around 96% efficiency, something very good. It is supplying for all India and also we are exporting the transformers. Hmm? This one. And if you look at the Russia, the Japanese, no, they're having 98% the efficiency. Of course, 2% doesn't matter here. This will be 96% is efficient. Something very good. It's a very good device, that one. So where that 4% gone in the transformer itself? Not I'm talking about cable. In the transformer itself, the 4% or 2% or 1% will be lost. Why do that happens here? So come for this structure. You see, like if you look at this particular coil here, no, some flux will be will come here also, no, in this region. This called a leakage flux. So what are the loss primary? What are the main sources for the losses in the transformer? The flux leakage. We cannot eliminate. We can minimize to some extent here, because see, like there's a B bar, no, you know, there's a current carrying like a ring. Some lines of force will come outside also here. If not many, at least few. Sir, but it's a solenoid. We know the field outside the solenoid should be zero. I know field is zero, but flux is non-zero. Getting the idea? The flux is non-zero. So some flux, this flux, what happen, which is coming here, will not link this. If it goes here, it's of no use here. So therefore, a flux leakage will be there. To avoid that flux leakage, what we should do? This particular wires, the windings, what happen, they should be closely spaced here. This is the one thing. And again, the copper wire which is used to which is used for as a winding, there's a copper wire which is used for winding. So what is the problem with the copper wire? It will offer some resistance, no? Because if current I flows through this red color or blue color wire, that itself will offer some resistance. It's a copper wire. And we know whenever a current flows through a metal, it should be generated. So there'll be heat. So to minimize this losses due to I square R in the windings, what shall I do? So go for R equal to rho L by A. So what sort of copper wire I should use for winding, which is more thick, no? If area of cross section is more, if I increase the area of cross section, resistance will decrease. If resistance decreases, I square R in the winding. So come out of that cable. So come out of this cable one. Come out of this cable. We are talking about now transformer. Come out of this cable. This only during transmission this will come. I'm talking about in the transformer itself. In the transformer itself, this wire is there, no, copper wire. When a current flows through that primary copper wire, secondary copper wire, heat will be generated, and the copper, this will have resistance. So what type of wire I should use to for winding purpose? Of thick wire. Area of cross section of more, resistance will be less. So I can minimize I square R losses in the copper wire. Flux leakage, and next is copper wire. Third one, what is this? This is iron, no? This is a thick iron frame. And here what's happening to current, varying current, and what happened to B bar? B bar also varies. Tell me, like what actually problem arises? Eddy currents are set up here, and eddy currents are set up here. So basically, I'll draw one diagram. I'll draw one rough diagram. You'll understand what is the meaning of 3D diagram. This should not appear, no? Okay, now. So what is this? If a B bar is varying, so we know the EP primary voltage we apply like this, sine omega t. Then what about current? Current also will be variable, I naught sine omega t. Then what happened to flux linking? Will be variable, no? Because that windings are here. What all that windings are there? These are the windings. Here the current flows like this. The B bar will be produced here. Look at the B bar. B bar will link, and so where do I'm showing this diagram? This diagram, so where it is here at this particular part, we are assuming a strip like this. We are assuming this strip. So that strip is there's a strip here. Able to understand now? So this strip, you look at this. The strip is what we assumed it. Now look at this. Inside, so how the B bar will be in this direction here. At this particular point, our B bar will be like this. So magnetic field B bar will be constant because we know B equal to mu naught n NP number of turns into current in the primary. B bar is also variable, no? Because of this B bar variable, and it's having area of cross section, say S. So what is the flux? B into S. B variable, S constant, flux is varying. As flux varies, then according to Faraday's law, E equal to d phi by dt. This everything is a conductor, no? Will there be any eddy currents? Yes, there'll be eddy current. How do that eddy currents? The eddy currents will flow. That's what the loop is telling that one. The eddy current will flow like this here. So you open the eddy current will make a loop. So what are these? These are eddy currents. The red color, these are eddy currents. Now, can we minimize eddy current? Can we ask eddy current not to flow? Because why do that? Because of free electrons, no? Can we ask free electrons not to move inside the conductor? Not possible, no? And heat will be generated. If you don't take care this, the efficiency of transfer will be only around 30%. 70% of the power will be eaten by the eddy currents only due to flow of eddy current. So it has to be taken care. Able to imagine this something like a when B bar, there's everything here. The current here, the flux will come like this here. Because of varying flux inside this core, eddy current will be set up here. Not on surface here, inside this one only here. So this what is showing the eddy currents, or still if you not able to understand, sir, eddy currents where they are, it'll be like this better. No. How to stop this eddy current flowing? So I will laminate it. Laminating the core greatly reduces eddy current here. So what do you mean by laminate? I will cut this. First a strip, then some a layer. Like this will happen. The core what happen will be laminated. Sir, what do you mean by laminated? I think you look at the loaf of bread. If you look at the bread, it's called as loaf of bread means this one, no? We are going to slice it, no? this called like a bread loaf, and one slice will be like this. One slice will come like this, no? This will be like this open. The core will be laminated. The core will be laminated. So sir, where can you show the slicing where you are done? The slicings are done like this here. And why the word lamination is brought? Lamination, photo lamination. What you do in that photo lamination? Like this, the core will be laminated. No. So what I do is I'll take a thin structure like this, a frame, thin frame. What is the thickness of this? Very small. Thickness of this will be very small. A thin frame, I'll take it. I'll take a thin frame. Then like that, some 100 or 200 thin frames, I'll join it. Then I'll get a thick core. Then what I do in between the frame, in between on the frame, so there's a one frame, no? I'll apply here a insulating material, which will not permit the current to flow. Insulating material. Then I'll paste another frame on this. Then in between gaps, what you get between the frame gaps open like a non-conducting substance. That non-conducting substance open will not permit eddy currents to complete the loop. The eddy currents wants to flow further, but open this non-conducting substance will not permit. So like this, what happen? The eddy currents will be minimized here. Earlier, the eddy current it wants to flow like this. So, but here what happened? This black color line. So what it is? It's like a non-conducting substance which will not permit the eddy current to complete the loop. If it doesn't complete the loop, what happens? The heat generated will be minimized. The eddy currents will be minimized here. So by like that laminating code, what do you mean lamination? First one frame, then I'll apply here some non-conducting substance on it. Then I'll place another frame on it. Then again another frame I'll put it. Then again on that frame laminating. So like that, if I join some 100 frames, I'll get a core. So there's a difference there. Here it's a non-laminated. Then many eddy currents will flow here. So here because of this open, the eddy current is confined only to this part you can see here. It got minimized. So practically it should be like this. Huh? He has shown some systematic way of diagram, but it should be like this. The eddy currents are plenty here. Here what the eddy currents are minimized here. Practically what it will be very thin, it will be made here. So eddy current, so here plenty will be there. What are that red color arbitrary circles? Eddy currents. Where it will be flowing like this here. So by laminating core open, we can minimize the eddy current. So this is the meaning of this. Also, I'm not understanding. You do one thing, notebook. In the notebook, what happened? The pages, between pages open, I'm going to put a conducting, like a non-conducting material. There's like a notebook, no? You can pick up that one. Between page two, in between pages open, I'll apply a non-conducting substance there, a thin layer, and I'll join the pages. So then definitely open the pages will not permit the eddy current to flow here, will not permit to complete a loop because a non-conducting layer will be present. So like this, by laminating core, what happen? We can eliminate the eddy current. So what are the losses? What are the losses? Losses are due to what? First one, flux leakage. This is the thing. Next year, resistance of winding wires. This is the thing. Third one, eddy currents. Flux leakage, what happen? I will do winding in such a way that I can minimize this flux leakage. Resistance of winding by using thick copper wires. We can avoid the I square R losses in the primary and secondary of the transformer. Eddy current by laminating the core. The fourth one, hysteresis. This is you can't understand now. We'll discuss this in magnetic chapter. The fifth one is humming sound. These things I'll discuss in magnetic materials because we need the different types of magnet and their behavior also. So time being 1, 2, 3 is what? The losses are there. The hysteresis losses and humming sound also. I think you stand nearby transformer, you get some sort of sound, no? This is called like humming sound. So these two I'll discuss in magnetic materials. We need idea of magnetic materials. I think just two formulas are there that you have to remember. Nothing else is there. And always the primary and secondary, they'll be in phase. The voltage across primary and secondary will be in phase. I think I've drawn it. This is very important. Check this graph. They will be in phase. The winding is such then it will be in phase. Okay, I'll stop the class. Okay, thank you all of you.